All right, welcome to the deep dive. Today, we're embarking on kind of a journey into some of the most fundamental parts of your body, the real unsung heroes. Imagine you've spent hours, poring over these dense medical texts, and now the real challenge hits. Explain it all to a curious 10-year-old. No jargon, just pure, clear understanding. That's really our mission today, right here, right now, as we dive deep into your body's hidden helpers and tiny task forces.
Yeah, you've really hit on something fundamental there. It's fascinating because we're looking at the body's actual architecture. How it holds together, how it moves, even how it defends itself. We'll be digging into supporting and connective tissues, and then the incredible world of blood cells. Think
Yeah.
of them like the unsung construction crew, and maybe the tiny vigilant police force inside you, laying the groundwork for, well, everything else.
Okay, great analogy. So let's start with that construction crew. Connective tissue. If your body was, say, a house, connective tissue would be the beams, the cement, the insulation, maybe even the packing peanuts.
Yeah, exactly.
It's the most diverse and widespread tissue, doing everything from, like, binding things together to providing strength, filling space, offering that crucial support and protection. It's basically the body's super versatile construction material.
Precisely. And here's an interesting thing. Unlike, say, skin cells that are packed really tightly, connective tissue cells are usually quite spread out.
Hmm.
They live within this amazing substance they actually create called the extracellular matrix, or ECM.
ECM, right?
So for our 10-year-old listener, you could think of the cells as the skilled architects and builders, and the ECM. That's the actual building materials, the bricks, mortar, maybe plaster that they make, and then live inside.
Okay, so who are these builders?
Well, the main ones are fibroblasts. They're the primary builders. Then you've got macrophages. They're like the cleanup crew. And mast cells. They're the alarm system, ready to raise a fuss if there's trouble.
Got it. Builders, cleanup, alarms. But what about the ECM itself? This living concrete they create. What's in that?
The ECM.
Yeah.
Yeah, that's where it gets really interesting. It has two main parts. This squishy ground substance, and then strong fibrillar proteins, the fibers.
Okay, squishy and strong. Let's start with squishy. Ground substance.
Right. Imagine it like a thick, hydrating gel, almost like jelly. It's highly polar, which means it just loves water and attracts it. In fact, it's usually about 90% water.
90%. Wow.
Yeah, and this watery gel quality is what makes tissues like cartilage so resistant to compression. Super useful when you jump or run.
So it's like a built-in shock absorber, a bouncy, watery cushion.
Exactly. That's a perfect way to put it. Its structure, for the med students listening, involves things called proteoglycans. Think of them like toilet brushes, a core protein with these long bristles called gags, glycosaminoglycans.
Toilet brushes. Okay.
Stay with me. These brushes then link onto these really long molecules called hyaluronate, forming these huge tangled structures. For the 10-year-old, imagine those toilet brushes are actually super, super absorbent sponges. When they all link together, they can soak up and hold tons of water. That's what makes the whole thing bouncy and squishy, perfect for cushioning and resisting squashing forces.
Okay, the toilet brush sponge analogy works. That's fantastic. Now, what about the strong part? The fibers. You mentioned collagen.
Collagen, yes. If the ground substance is the cushion, collagen is like the steel cables holding everything together.
Steel cables.
It's actually the most abundant protein in your body. It makes up something like 30% of your total protein.
30%. That's incredible.
It really is. And these steel cables are built with amazing precision. Each tiny unit is a triple helix structure called tropocollagen. These little helices line up end to end and side by side, assembling into fibrils. Fibrils bundle into larger fibers, and fibers group into massive bundles. You see these big bundles in things like tendons. And there are many types, but type I is the workhorse. It's about 90% of all your collagen found in tendons, the deep layer of your skin, the dermis, bone. There's also type 4, which is interesting because it forms sheets, like a flat mesh, found in the basal lamina, which is like a foundation layer for epithelial cells.
Okay, so these cables are incredibly important, but how are they made? And what happens if they're faulty?
That's a really critical question. Making these ropes is complex, starts deep inside the cell, in the rough ER. And something like vitamin C is absolutely crucial. It helps stabilize and strengthen the collagen structure.
Vitamin C. That's why sailors got scurvy, right?
Exactly. Without enough vitamin C, you get scurvy. Collagen can't form properly, leading to things like gum ulceration, poor wound healing. And then there are genetic conditions where collagen synthesis goes wrong, like Ehlers-Danlos syndrome. Different types affect different collagen types. For instance, a defect in type 3 collagen, seen in vascular Ehlers-Danlos, can weaken blood vessels. potentially leading to catastrophic aortic rupture.
That sounds terrifying.
It can be. And then there's osteogenesis imperfecta brittle bone disease. That's often due to mutations in the genes for type I collagen, the main type in bone.
So this really drives home the point. If the fundamental beams or cables aren't right, the whole structure suffers. It's not just academic, it has huge real-world consequences.
Absolutely. Microscopic details with massive impacts. But, not all fibers are just about brute strength.
Right, you need stretch too. So if collagen is the steel cable,
Then elastin is the super stretchy rubber band.
perfect. It lets tissues stretch out and then, importantly, snap right back to their original shape, like in your skin, right?
Yep, your skin, walls of large arteries that need to expand and recoil with each heartbeat, places that need that elasticity.
And how does that work? What's it made of?
It's actually a composite. You have the elastin protein itself, which provides the stretchiness, deposited onto a scaffold made of another protein called fibrillin. Fibrillin microfibrils kind of organize the elastin.
Okay, so fibrillin is the scaffold for the rubber band.
You got it. And just like with collagen, if you have problems with elastin or that fibrillin scaffold, you get serious conditions.
Such as?
Well, Marfan syndrome is a classic example. It's caused by a mutation in the fibrillin-1 gene. People with Marfan are often very tall, have loose joints, maybe lens dislocation in the eye, and critically, they're at risk for aortic aneurysm or rupture because the elastic walls of their aorta are weak.
Wow, all from one scaffold protein issue.
Exactly. And then there's Williams syndrome, where part of a chromosome, including the gene for elastin itself, is deleted. This often leads to cardiovascular problems, developmental issues, again highlighting how vital that stretchiness is.
It's truly amazing how these microscopic components build up to create tissues with such different properties. Strength, stretch. Now, where does all this connective tissue originally come from? Who are the master builders?
Good question. It all traces back to the embryo, to special master builder cells called mesenchymal cells. These cells are multipotent, meaning they have this incredible ability to differentiate, to become many different types of connective tissue cells. Bone cells, cartilage cells, fat cells, fibroblasts.
So they're like the ultimate stem cell for structure.
Pretty much, yeah. And what's really cool is that even as adults, we retain some similar cells, often called mesenchymal stem cells or stromal stem cells, in various tissues. They hang out in places like bone marrow and fat tissue, and they play a crucial role in tissue repair and regeneration throughout our lives.
That's fascinating. A built-in repair crew from the original builders. Okay, so we had the building blocks. Let's look at the main types of connective tissue proper. You mentioned loose and dense.
Right, we can broadly categorize them based on how densely packed the fibers are. First, there's loose connective tissues, sometimes called areolar tissue.
Loose, so like the fluffy packing material.
That's a great way to think of it. Fluffy packing material, or maybe soft bedding. The fibers collagen, elastin, reticular fibers are loosely arranged. There's plenty of ground substance, lots of space.
Where do we find this fluffy stuff?
It's actually really common. It's right under your skin, the superficial fascia, which allows your skin to slide around a bit. It's also found around glands, blood vessels, nerves.
Yeah.
It basically fills spaces and supports these structures. It contains various cells like fibroblasts, macrophages, mast cells. It often forms the stroma, the supporting framework of many organs.
Okay, makes sense. And within this loose category, I remember something special.
Yes, adipose tissue, or fat. It's considered a specialized type of loose connective tissue.
Ah, fat, more than just energy storage.
Oh, absolutely. It's
Yeah.
crucial for energy storage, yes, but it's also insulation, keeps you warm. It's protective cushioning. Think of the fat pads around your kidneys or behind your eyes, and it even helps shape the body.
And there are different types of fat.
Primarily two. White fat is the most common type in adults. Under the microscope, the cells often look like signet rings because the large fat droplet pushes the nucleus to the side. This is your main fuel reserve, insulation, shock absorber. Then there's brown fat. It's much more common in babies, though adults retain some. It looks brown because it has a really rich blood supply and tons of mitochondria.
Mitochondria, the powerhouses. So brown fat does something different.
It does. Its main job is generating heat. It performs something called non-shivering thermogenesis. Basically, it burns fuel to produce heat directly, helping keep babies warm without them needing to shiver.
Wow, built-in heaters. Okay, so that's loose connective tissue in its special fat variant. What about the other category, dense connective tissue?
Right. If loose tissue is fluffy packing material, dense connective tissue is like super strong cables or reinforced mesh.
Okay, much tougher stuff.
Definitely. Here, the fibers, mostly type A collagen, are much more densely packed,
Mm.
and there are fewer cells and less ground substance compared to loose tissue.
And there are different arrangements here, too.
Yes, two main types based on how the fibers are arranged. First, dense, irregular connective tissue.
Irregular. So messy.
Not messy, but interwoven. Think of it like a strong, woven mesh, or maybe a basket weave pattern. The collagen fibers run in multiple directions
Why would you want that?
because it allows the tissue to resist strong pulling forces from many different directions. Think about the deep layer of your skin, the dermis. It needs to resist stretching and tearing from all angles.
Ah, okay. Makes sense. Where else?
You find it forming tough capsules around organs, like the liver or spleen. It's in the periosteum around bone, the perichondrium around cartilage, and even the dura mater, that tough layer protecting your brain and spinal cord.
So strong and multidirectional. What's the other type?
That would be dense, regular connective tissue.
Regular. So this one's neat and tidy.
Exactly. Here, the collagen fibers are densely packed and arranged in parallel bundles, all running in the same direction.
Like perfectly aligned cables.
Precisely. This provides tremendous strength against pulling forces in one specific direction.
And where do you need that kind of unidirectional strength?
Tendons. They connect muscle to bone. They need to transmit the strong pull of the muscle in a straight line to move the bone. Also, ligaments, which connect bone to bone, stabilizing joints.
Right. So tendons and ligaments.
And if you look closely at dense, regular tissue, you'd see the fibroblasts, those builder cells, kind of squashed flat between the massive parallel collagen bundles. These bundles often group together into larger units called fascicles. It's a very organized, very strong structure.
Any variations here?
Well, some ligaments, called elastic ligaments, like the ones in your neck that help support your head, or between your vertebrae, contain a higher proportion of elastin fibers mixed in with the collagen. This gives them extra stretch and recoil ability.
Okay, that covers the body's scaffolding and glue pretty well. Amazing stuff. Shall we move on to the tiny task force? The blood cells.
Absolutely. Let's shift gears to the body's internal transport system and its defense network. Blood. You have to imagine this bustling factory, deep inside your bones specifically, the red bone marrow in adults. This factory is constantly producing all the different types of cells that circulate in your blood. The whole process is called hematopoiesis.
Haematopoiesis. The blood cell factory.
Exactly. And remarkably, all blood cells, red cells, white cells, platelets, originate from a single type of ancestor cell, the pluripotent hematopoietic stem cell.
One stem cell makes everything.
Pretty much. It's incredible. Early in fetal life, this happens in the yolk sac, then it shifts to the liver and spleen, and finally, around birth and afterwards, the bone marrow takes over as the primary site.
And how does it decide what to make?
Well, that stem cell gives rise to two major lineages, two main production lines. There are myeloid stem cells,
Okay.
which lead to red blood cells, most types of white blood cells called granulocytes, monocytes, and also the cells that produce platelets.
That's a lot from one line. What's the other?
The other line is the lymphoid stem cells. These give rise to the lymphocytes, the B cells, T cells, and NK cells, which are key players in the immune system. It's a really organized process, like a branching tree.
Got it. Two main branches from the master stem cell. Let's follow the myeloid line first. Red blood cells, RBCs. You call them oxygen delivery trucks.
Yep. Erythrocytes is the technical term.
Erythrocytes. Okay.
Yeah,
They're like tiny, flexible delivery trucks. I remember the shape is weird.
it is. They're biconcave discs. Think of a donut, but the hole doesn't go all the way through. It's indented on both sides.
Why that
It
shape?
gives them a large surface area for gas exchange, and it makes them incredibly flexible so they can squeeze through the tiniest blood vessels, the capillaries, which are sometimes narrower than the RBC itself. They're about 7.2 micrometers across, normally.
And they ditch their nucleus?
They do. Mature RBCs in mammals have no nucleus, no mitochondria, no ribosomes. They basically eject all that stuff to make more room for the main cargo. Hemoglobin. Each RBC is jam-packed with it, about 270 million molecules per cell. Hemoglobin is a protein that actually binds and carries oxygen from your lungs to your tissues. It also helps carry some carbon dioxide back.
270 million. Wow. And how long do these trucks last?
They have a pretty defined lifespan, around 120 days. After that, they get old and worn out, and they're removed from circulation, mostly by macrophages in the spleen and liver.
And how does the factory know when to make more?
Good question. The trigger is oxygen levels. If your tissues sense low oxygen, a state called hypoxia, your kidneys, and liver to some extent, release a hormone called erythropoietin, or EPO.
EPO, I've heard of that.
Right. EPO travels to the bone marrow and basically tells the myeloid stem cells, hey, we need more red blood cells. Ramp up production.
So for a 10-year-old, if you run really hard and get out of breath, your body sends a message, more oxygen trucks needed.
That's a great way to explain it.
And if something goes wrong with these trucks, if they're broken or you don't have enough or maybe too many.
Yeah, that leads to various disorders. If the hemoglobin is faulty, like in sickle cell anemia, the cells become misshapen and can block blood flow. If you don't have enough RBCs or hemoglobin, that's anemia like iron deficiency anemia, which is very common, makes you feel tired and weak. And if you have too many RBCs, that's called polycythemia. It makes the blood thicker, which can increase the risk of clots.
Okay, vital trucks need the right number and they need to work properly. What else comes from that myeloid line? Platelets.
Yes, platelets or thrombocytes. If RBCs are delivery trucks, platelets are the body's rapid response repair crew.
The sticky Band-Aids.
Yes, the sticky Band-Aids that stop bleeding. They're not actually whole cells, but small, irregular-shaped fragments of cytoplasm, about 2-3 micrometers across.
Fragments, where do they come from?
They bud off from huge cells in the bone marrow called megakaryocytes. These giant cells sit near blood vessels and extend little arms of cytoplasm into the vessel, and bits just break off. Those are the platelets.
Wow, and they don't have a nucleus either.
Nope, no nucleus. They have granules filled with clotting factors and other chemicals. They have a much shorter lifespan than RBCs, only about 8 to 12 days.
And their job is clotting.
Primarily, yes. When a blood vessel is damaged, platelets rush to the site. They stick to the damaged area and to each other, forming a temporary plug. They also release chemicals that attract more platelets and start the cascade of reactions involving clotting factors, which are proteins mainly made by the liver, that leads to a stable fibrin, clot this gap.
So next time you get a paper cut, these tiny fragments are the first responders plugging the hole. Incredible teamwork.
It really is. And again, numbers matter. Too many platelets is thrombocythemia, which can cause unwanted clotting. Too few is thrombocytopenia, which leads to easy bruising and bleeding.
Okay, RBCs for oxygen, platelets for repairs, now for the defense force, the white blood cells, or WBCs, leucocytes.
Right. The body's dedicated immune army. And just like any army, it has different types of soldiers, each with specialized jobs to keep you healthy.
An entire military force inside us. Let's meet some of the key players. You mentioned monocytes coming from the myeloid line.
Yes. Monocytes are the largest type of WBC. They have this characteristic kidney-shaped or horseshoe-shaped nucleus. Think of them as patrolling police cars circulating in the bloodstream. They're out there looking for trouble.
Patrolling cars. Okay. What happens when they find trouble?
Well, they don't usually stay in the blood for long, maybe 20, 40 hours. Then they migrate out into the tissues. Once they enter the tissues, they transform and mature into macrophages.
Macrophages, the big eaters.
Exactly. Macro, big, phage, eat. These are like the local police detectives, or maybe the heavy cleanup crew, stationed within the tissues. Their main job is phagocytosis, engulfing and digesting cellular debris, foreign invaders like bacteria and old cells.
So they eat the bad guys.
They do. But they also play a crucial role in immunity. They act as antigen-presenting cells. They basically show pieces of the invaders they've eaten to other immune cells, like T lymphocytes, to say, look what I found. We need to mount a specific attack against this. They also release chemical signals, cytokines, that help orchestrate the immune response and inflammation.
So they're eaters, presenters, and signalers. Very versatile. Do they have special names in different tissues?
Yes, depending on where they reside, they get specific names, like Kupffer cells in the liver, microglial cells in the brain, alveolar macrophages in the lungs. But they're all fundamentally macrophages doing similar jobs.
Fascinating. Okay, who else is in this army? You mentioned granulocytes from the myeloid line.
Right. Granulocytes are named because their cytoplasm is full of prominent granules, which are like little sacs containing various enzymes and chemicals. There are three main types.
Okay, let's hear about them.
First, neutrophils. These are the most numerous type of WBC, making up maybe 50–70% of the total.
The first responders? The SWAT team.
That's a perfect analogy.
Yeah.
They have a distinctive multi-lobed nucleus, looks like several blobs connected by thin strands. They're absolutely the first cells to migrate out of the blood vessels towards a site of acute inflammation or infection, especially bacterial infection. They're attracted by chemical signals, a process called chemotaxis.
And when they get there?
They phagocytose bacteria and debris like crazy. They're essential for fighting off bacterial infections quickly.
Right.
They don't live long, though. Maybe 10 hours in circulation and a day or two in tissues. Pus is largely made up of dead neutrophils.
Wow, short-lived but crucial. Who's next in the granulocyte team?
Eosinophils. These have a bilobe nucleus, and their granules stain bright red or pink with eosin dye, hence the name.
The allergy and parasite detectors.
Exactly. They're not as numerous as neutrophils, maybe 1–4% of WBCs. They are important in fighting parasitic infections like worms. Their granules contain enzymes that can damage the surface of parasites. They also play a role in allergic reactions, helping to modulate the response, but sometimes contributing to the inflammation.
Okay, parasites and allergies. And the third, granulocyte.
Basophils. These are the least common type, less than 1% of WBCs. They have large, dark, purple granules that often obscure their nucleus.
Oh, alarm bells.
Yes. Their granules are packed with histamine and heparin. When they get activated, usually during allergic reactions or inflammatory responses, they release these mediators. Histamine causes blood vessels to dilate and become leaky, leading to swelling, redness, itching, the classic signs of an allergic reaction.
So they sound the alarm, but sometimes maybe a bit too loudly.
Exactly. They're closely related to mast cells, which are found in connective tissues, not usually in blood. Mast cells also release histamine and are major players in allergies and anaphylaxis. Basophils circulate, mast cells reside in tissues, but similar function.
Okay, that covers the granulocytes, neutrophils, eosinophils, basophils. Now, what about the other main branch from the stem cell, the lymphoid line?
Ah, yes, the lymphocytes. These are the specialists, the intelligence and adaptive combat units of the immune system. They typically have a large, round, or slightly indented nucleus that takes up most of the cell, with just a thin rim of pale blue cytoplasm.
Specialists, so different kinds of lymphocytes.
3 main types: B lymphocytes, T lymphocytes, and natural killer NK cells.
Let's start with B lymphocytes, B cells.
Okay, B cells mature primarily in the bone marrow. That's where the B comes from. Their main role is in humoral immunity, which means immunity involving substances in the body fluids, specifically antibodies.
Like antibody factories.
Precisely. When a B cell encounters an antigen, like a protein on a bacterium, that matches its specific receptor and gets the right signals from other immune cells, like helper T cells, it gets activated. It then proliferates and differentiates. Many become plasma cells. Plasma cells are true antibody factories. They churn out huge amounts of specific antibodies that circulate in the blood and lymph.
Like chemical weapons targeted at the invader.
Exactly. These antibodies can neutralize toxins, coat bacteria to make them easier for macrophages to eat, or activate other parts of the immune system. Other activated B cells become memory B cells, which live for a long time and provide immunological memory, allowing for a faster, stronger response if you encounter the same invader again.
Okay, B cells make the antibodies. What about T lymphocytes, T cells?
T cells mature in the thymus gland, hence the T. They are responsible for cell-mediated immunity, meaning they act more directly on other cells.
The strategic commanders and trained assassins.
Good way to put it. There are 2 main types of T cells, distinguished by proteins on their surface called CD markers. First, you have CD4 plus T cells, often called helper T cells. These are the commanders. They recognize antigens presented by other cells, like macrophages or B cells. When activated, helper T cells don't usually kill invaders directly, but they orchestrate the overall immune response. They release cytokines that activate B cells to make antibodies, activate macrophages to kill better, and activate cytotoxic T cells. They're essential coordinators.
So they direct the traffic and rally the troops. What about the assassins?
Those are the CD8 plus T cells, or cytotoxic T lymphocytes, CTLs. These are the trained killers. Their main job is to recognize and kill host cells that are infected with viruses or other intracellular pathogens, or cells that have become cancerous.
How do they kill them?
They can induce the infected cell to undergo programmed cell death, apoptosis, or they can release proteins like perforin and granzymes. Perforin punches holes in the target cell membrane, and granzymes enter and trigger cell death. Very targeted killing.
Wow, direct cellular combat. So B cells for antibodies, T cells for coordination and direct killing. What was the third type of lymphocyte?
Natural killer cells, or NK cells. These are a bit different. They're part of the innate immune system, our first line of defense, whereas B and T cells are key players in the adaptive immune system, which learns and remembers specific pathogens.
Innate, so they don't need prior activation.
Largely, no. They don't recognize specific antigens like B and T cells do. Instead, they can recognize and kill cells that are showing signs of stress, like virus-infected cells or tumor cells, often because these stress cells stop displaying certain self-markers on their surface.
The vigilant guard dogs, taking out suspicious characters without needing specific orders.
That's a pretty good analogy. They provide an important early defense against viruses and cancer before the adaptive immune system fully kicks in.
Okay, B cells, T cells, helper and cytotoxic. and NK cells. An amazing array of specialists. And when things go wrong with these cells,
That can lead to serious diseases. Cancers of the lymphoid lineage are known as lymphomas if they form solid tumors, often in lymph nodes, or leukemias if the cancer cells are primarily in the blood and bone marrow. These can involve either B cells or T cells.
right. So we've covered the scaffolding and the task force, connective tissues giving structure and support, blood cells handling transport, repair, and defense.
Exactly. And we connect this all back for our future medical students. You can really see how interconnected it all is. You need the right structure provided by connective tissues for everything else to function, and you need the dynamic defense and transport capabilities of blood cells circulating within that structure. It's this incredibly intricate, beautifully choreographed dance happening constantly inside us.
So what does this all mean for you, our listener? Whether you're that first-year med student or trying to explain this to a 10-year-old, it means that these parts of our body we rarely think about, the microscopic details, are performing these absolutely incredible life-sustaining jobs every single second. These hidden helpers, like fibroblasts and the ECM, these tiny task forces like neutrophils and lymphocytes, they are the silent architects and the vigilant protectors, keeping everything running smoothly. They are quite literally the fabric of our existence. And maybe here's a final thought to chew on, something to think about later. We mentioned that those mesenchymal stem cells, the original master builders, persist throughout life as stromal stem cells, constantly helping to renew our connective tissues.
A key point for repair.
Right. So what might that imply about the future? Thinking about regenerative medicine, about potentially healing some of these really tough disorders we touched on, the ones affecting collagen or elastin, or maybe even regenerating tissues after injury. It's a powerful idea, isn't it? Could we one day really harness these internal master builders, our own stromal stem cells, to truly rebuild parts of our bodies from the ground up? Something to ponder.